just change that and then now I have to move my next slide.
All right, we're gonna start today looking at the generator that is basically ready to go. So we're gonna spend first chunk talking about the current assignment and answering questions, because the more that I fielded questions on this, the more that I realized that there's ambiguity and or people don't really know how to proceed in certain areas. And some of that is just that there wasn't a world generator, and some of that is that there are misconceptions surrounding the rules of the Wumpus world in general. So we're gonna start talking about that, and then once we've exhausted talking about that, we'll dive back into content. So let's start here. So we have a world generator that we can use. How do we use it? So basically, this is going to be attached to Canvas for you to download and use. What you are responsible for is the associated rule creation and agent behavior. So the rule creation is going to be within this natural language toolkit, and the agent behavior is going to be a script that talks to that. You're going to, at the very beginning of your program, tell the knowledge base everything about the world, all of the state of the world, and then you're going to interact in that environment in such a way. So we're going to have a world that's attached to that run. Now the agent is going to decide from the very beginning, what do I do and how do I get information about the world from that? Can I assert that this particular cell is safe given the information that I have historically in the knowledge base? The knowledge doesn't ask to the knowledge base that the knowledge base can return true or false to, or unknown. And that allows you to determine, okay, how should the agent path to that? We're going to use there's pseudocode on one of the slides that you should implement. That allows the agent to know what it should be doing at that point, plan ahead to, I want to move from this location to that location because I know that that location is safe, so I'm going to go explore it. Great. Then you'll go do that, utilizing any knowledge that you gain along the way in terms of tells to the knowledge base. Once you reach there, maybe there's a breeze in that location. You can add that to the knowledge base and then query, are there any adjacent safe unvisited cells? And you would have the predicate logic to be able to return, here is the list of safe unvisited cells for which you could pick one and go explore that. You just want to make sure that you only path through safe visited cells as you do it, and not just find a general shortest path, because the shortest path might be through some dangerous or not necessarily safe locations.
Your report.
Yeah. So what you're not responsible for is generating a world. So that's what's going to be given to you. So when this program runs, your agent should be able to attach itself to an unknown world seed and intelligently go find the gold. If the gold is there, you don't have to worry about anything probabilistic. If the safety of a particular cell is unknown, don't go explore it. Maybe more information you get as you explore around will remove that ambiguity and allow you to determine whether it is safe or not. But do not take any probabilistic action at this time, because we have not talked about how to deal with that probabilistic nature, and that will come later. So for now, just if there is some safe unvisited cell for you to explore it until you find the gold, and then get out. And remember that the agent always spawns in the same location, 1-1, bottom left corner. Its orientation is facing right or east, however you want to do that. And that's where the agent has to go in order to escape. So to terminate the episode, you have to redirect your agent back to that starting location and choose the action climb. And that terminates the episode. So if I'm going through and doing this, like you all are, what I am focusing on is coming up with all of the logical rules to feed the knowledge base initially. What are the associated rules of the Wumpus world? The reason we're doing this is because if you don't state the rules correctly, then your agent is going to do silly things like be able to walk right over pits and go find the gold without dealing with pits at all. And while that maximizes the score that you would get, it does not represent the system that you are in. And if you are responsible for a security related system, you would want to make sure that you have all of the rules of that system represented. You don't want the equivalent of walking over pits to get the gold. This is the equivalent to me of a program saying, we have not experienced a breach in 20 years. And of course, everyone's password is on the dark web. It's actually happened. But because your program didn't catch it, it has excellent performance according to your own internal metric. We want the ability to recognize a metric to match with the associated rules of the system. And so that's why we're using a knowledge base agent for this, so that we can find and get experience with making a rule-based system and incorporating those rules into your knowledge base. Otherwise, you're expecting there to be some program out there that tells you you've fallen into a pit, bad, -1000. If that doesn't exist, how do you create that system, recognize that system, and make intelligent actions within that system? So that's why you're going to have a Python script agent and a knowledge base of those basic rules. Your agent can ask the knowledge base for information, utilize that information to make decisions. Does that make sense? So your agent shouldn't be storing things like whether something is safe or whether something is visited or anything else of the sort. That's all in the knowledge base. The agent should only be responsible for doing actions like moving forward. And the knowledge base is going to store, it's the brain of the agent. It's going to store all of the information for making those decisions. All right, so how does this world generator work?
So it essentially creates a 2x2 array full of, like it's a 3x3 array, but each 2x2 array, each cell has, whether there's a breeze, a wall, your explorer, whether there's a pit there, etc. You can export this to JSON, so that way you can save it for later. You can import it from JSON. JSON looks like this. It's just a big 2D array or array of arrays. And this code, mainly it just has a way for you to visualize it. If there's any overlap, like they say there's a pit and a breeze, like maybe two pits are next to each other, there would be a breeze on top of a pit. You can change the render ordering so you can render the breeze on top. But you can see this world, in the top left we have the explorer, then there's a pit. I have it set where it's by default where black is pits, white or bluish is breezes. The green that shows up, it's not really green. The upper right green is the lumpus. And the bottom left one is the gold. With the green, with the darker green around the lumpus being the stash. So you can visualize the worlds you make. If you would like, by default, it's based on the book's specifications. The hits have probability of spawning of 0.2. You can set a seed if you want. You can set the world dimensions, and if you would like to go in and edit it, there's the JSON. There's not really a clean way to edit it without just like going piece by piece. If you wanted to go piece by piece to design something to mess with somebody's agent.
Yeah, so the idea, I think, is that we wanted a visualizer so that it aids in testing your agent. So as you're adding things to the knowledge base and you reach a point where you think, all right, I want to test this, then you will create a test world with this. Then my hope is that you can debug while you have the world open so that you can see what the list of exactly what actions your agent chose to do. And then you can run debug step by step. How did they make those associated actions? And you can follow along visually in the world that is there, that's generated, and you can get a sense of if the agent did something that doesn't make sense to you. There are two reasons that might be. Either the agent decision maker has a bug in it and it chooses the wrong action, or there's an issue with your knowledge base where the agent, given what's in the knowledge base, made a very intelligent decision, but there's an issue with either the initial information that you put in your knowledge base or with your forward chaining, backward chaining a resolution that we'll talk about today with ways of generating new information. Did it generate something that was false? Is the logic wrong somewhere in that? This would allow you to be able to see what your agent did and kind of what it should have done because you have a more visual sense of the world to help aid in that debugging. I also wanted to remove ambiguity about the rules of the Wumpus world. So those are on the slides, but from talking to people, I've gotten a sense that people don't have a great sense of the rules of the Wumpus world. Does anyone have any questions about how this works or assumptions that you're making that aren't necessarily based on information that is directly pulled off of a slide that I can clear up?
I had something to point out that I had a misunderstanding with Chris. You guys are making not only the agent that explores the world, but also the world rules.
Yes.
As in, like, you die in a pit, you die if you touch the Olympus, you shoot an arrow, that kind of thing.
So all of the, on the slides, we talk about representing logic in terms of both propositional or predicate logic. You'll want to take the predicate route for this just about all the time. But yes, the idea is that you're representing a rule-based system. Otherwise, there's no reason to use a knowledge-based agent. It just becomes another way to write the same kind of script that you could write in Python for the agent behavior. And the agent behavior is an important part of it, but the actual knowledge of the world, the rules associated with the world, I think is also an important part. And it really shows the power of a knowledge-based agent. Whereas if I forced you to use the knowledge-based agent without that, everyone in here would say, can I just write a script for this? It'd be faster, it'd be better. And I don't want that without the ability to see why we're using it, which is that it can represent all of the rules of the system as the input to it. Other questions or clarifications? Yeah.
So the rules of the world have to also be in predicate logic.
Yes.
So you shoot an arrow. You have to write the predicate logic for the arrow to go the whole spaces moving forward.
Yeah, like does the Wumpus die? All you have access to is the state of the world. It tells you where the Wumpus is, but your agent isn't going to know that.
Yeah,
Your agent has to logically determine where everything is and the associated rules of if I shoot an arrow in the direction of the Wumpus, then the Wumpus dies.
but I assume
Yeah.
the arrow goes more than one space.
Yes, yeah, it shoots all the way until it hits a wall or a Wumpus.
Yeah, okay.
So if you know where the Wumpus is, or have a really good guess as to where the Wumpus is, your agent can decide to spend 10 points to shoot the arrow in that direction, see if it hears a scream, and based on that can make a decision about, should I go now ignore stenches? Because stenches no longer have any meaning after the Wumpus has died. So your agent should know now to ignore that. That has to be encoded into your agent, as well as the logic for if I feel a breeze, then somewhere adjacent to me there is a pit.
I have a question.
Yeah.
Say that we kill, or the agent kills the Wumpus.
Yep.
Right? Does that then remove the stench from,
No,
no, so
the stenches will stay, and you will experience those stenches as the agent, but you should ignore them because they no longer have meaning.
Okay,
It's now a rotting Wumpus rather than a smelly Wumpus.
so we would include that in.
Yes, a rotting Wumpus will not eat you. A smelly Wumpus will eat you.
I'm sure nothing in the world changes except for taking the gold.
So,
Yeah.
but then that removes glitter.
I guess that too, yeah.
Yeah, okay.
Can the gold show up in 1-1? Cell 1-1.
That is a very good question. As far as I'm aware, the answer is no.
I don't think it.
Yeah.
I-
So in 1-1, we know there is no pit, we know there is no Wumpus, and we know there is no gold. The agent is basically guaranteed to be in an empty safe square on creation, and then every other square could have anything relating to a pit, a Wumpus, or gold. So if you immediately feel a breeze from 1-1, there is no safe cell to go visit. You should just immediately climb. Now, eventually we'll talk about how to analyze this probabilistically and make informed decisions about how likely are we to be able to find the gold, given how likely a particular unknown is to contain a pit. But don't worry about that yet. Anything probabilistic, just if there's no safe cell, then just
Exit.
abort, go back to the 1-1, exit.
A wumpus also cannot exist on a pit cell, right?
As far as I am aware, that would be a very weird floating wumpus. In which case you could either die to the pit or die to the wumpus, yeah. If there is the case where a pit can be on top of a wumpus, that should not change the agent's logic.
But what if the Wumpus is bigger than the pit? You kill the Wumpus. It's safe to go over that.
That would be an interesting way of thinking about it. Yeah, for now, we will make no assumption about whether a wumpus and a pit can exist in the same location. So your agent should not make an informed decision about whether a cell is safe based on the knowledge that they can't be in the same cell or they can be in the same cell. Worst case then. Other clarification questions on it? Does this help to clarify exactly what your role is in this project, as well as the rules of the system clear?
I think so. So the agent is about interaction, and then we have this probably like a separate file to define rules.
Yeah, your knowledge base is going to be a natural language toolkit
So,
instance.
so whenever an action is made by the agent, it will then interact with the rules.
Yeah, so the agent is going to experience its percepts, and then it can tell the knowledge base everything that it perceives. I am here at this time, and here are my percepts. And the knowledge base can either say, I already knew that, or this is new information. And then when you ask the knowledge base, it can utilize logic to, if there's new information there, then it can tell you something.
So if the agent grabs a goal, that's the action. Then removal of the glitter, that's the world, then, right?
Right.
Okay.
Yeah, your knowledge base, somewhere in your knowledge base, you would want to say, if the last action was grab, then the cell no longer gives glitter.
So your knowledge base is your world.
It's, yeah, your knowledge base contains your world rules. And what you're gonna do initially is you're going to add all of the logic for the world. Just gonna dump everything that you know about the associated rules without any knowledge of the current world. The world is there for you to visualize because that's the ground truth. For you, the engineer, to be able to determine, is my agent performing? Because the agent cannot see the entire world, but you can see the entire world to debug the agent. It has to explore just with the percepts that it gets while it explores the area. And then you can determine, is what it's doing intelligent and logical based on the knowledge that it has? And is it adhering to the rules of the Wumpus world? Anything else?
You just shoot a prayer for me personally. This is something that we do. I'd appreciate that.
There's a bit here. If I have to extend this a little bit, I'm more than happy to do that based on how long it's taken to get a reasonable world generator together, and just that this is a little bit more involved. Yeah,
Do we have like the explicit rules posted somewhere?
they're in the slides.
They're in the slides?
Yeah.
I was looking around.
I could put them in the assignment, yeah.
We make this the final for the class and we don't meet until the end, other than to ask questions.
So we can all do it the week of finals instead
Shut
of
up.
next week.
You give students an amount of time to do something, they will, however long it's going to take, or they think it's going to take, they will cram that at the very end of
No, that's not
that
true.
period of time.
That's not true, Chris Kenny.
Gosh, you're kidding.
I've already.
Yes.
Querying my knowledge base, it returns that that is bullshit.
I gotta update the file or something.
Pro.
That's.
Yeah, yeah. Yeah.
And
That's
then,
perfectly fine. It's not ready to go, but you can throw it on the assignment once it's ready to go.
cool.
Cool. Yeah,
Just to clarify one last time, the agent is also built using the toolkit.
the agent can be its own Python file if you want. It doesn't have to be in the toolkit itself. So your agent can define some of the if statements, basically in the slide that has the knowledge base agent. It basically says if percept glitter, then grab gold. So all of the agents kind of if then rules, that's going to be its own file. But the knowledge base is going to be able to say something like, is this cell safe? Have I visited this cell before? Is there a reasonable path from here to there through safe only cells? Those kinds of questions that we want to be able to ask the knowledge base should be able to figure out with the associated logic that it has. And that will return something like the agent can determine what the next action to take is based on the knowledge stored in the knowledge base.
So the knowledge base is its own separate Python script that builds on itself.
Yeah, so you can think of the agent kind of like your body, and the knowledge base is like your brain. Your brain tells your body, do these things, but the brain is not capable of doing those things. It has to communicate to the body, to the muscles to actually go do that. So your agent has the ability to do that. The knowledge base tells you whether it's a good idea or not. I could throw myself out the window, but the knowledge base tells me that that would be stupid.
And the knowledge base has both the background hidden knowledge of the actual world as it is, and then builds on precepts that the agent.
Yeah, so as the agent experiences things, it's going to communicate that over to the brain that says, there's a breeze in this location. And then based on that, the knowledge base can determine there's a pit in this location because there wasn't a breeze in this other location. That's not phrased in terms of if-then rules, you're using forward chaining, backward chaining, or resolution to figure that out from the knowledge that's in the knowledge base. So you're not writing procedural or OO code, you're using logical inference to be able to return that idea to the agent program. And that will help the agent to figure out, what do I do next, knowing that you could ask the knowledge base, is there a safe unvisited cell? And it might return to you, no, in which case the agent then says, I should get out of here.
Does the agent update the knowledge base as it goes, or
Yes.
does the knowledge base have access to the?
The agent will be telling and asking the knowledge base as it explores.
Okay,
So you start with just all the rules of the Wumpus world.
Yeah.
And the initial percepts of the agent in 1.1. Then the next question is, what should I do from there? If there's no breeze, I can just go forward. I know that there's no stench. The 1.2 is guaranteed to be safe. So I can go do that. Based on what's there, it just kind of branches from there as to what is the nearest safe unvisited cell.
And you said if there's like nothing, like if you'd have to take a gamble to move, then you just
Don't.
leave. Okay.
I don't care if it's a 1% chance. Don't gamble. I know that's hard for getting.
Actually,
This
watched
class.
all of Thomas's money disappear on a poker
I
game.
don't want to talk about it.
I had a problem.
Daniel did not have all his money disappear.
So I thought based on like 2 minutes of playing the night or this weekend that I was just really good at poker. And then I sat down and I actually played poker.
I think Thomas realizes looking at your phone to see what hand you have is a dead giveaway if you have. We'll get there.
But you gotta take the.
Man, it sounds really profitable to play poker with Thomas.
You should.
It is. I actually, you're gonna be so proud of me, Chris Kane. I realized that the answer is just not to play.
Wow.
Yeah.
Oh,
I'm still going to play because I'm gonna get pressured into it. But then it's like, it's not playing to play, it's just playing to spend time with my friends.
Yeah.
That now I have to pay for some reason.
Okay.
Yeah.
So regarding the world rules, I assume primarily that that's all gonna be using the NLTK library.
Yes.
Right?
All the logic is gonna go through that. Any proposition, any predicate logic. And tells and asks are going to utilize.
So the agent is free to use, assuming standard,
Yes.
okay.
Yeah.
It doesn't have to use the end.
Yeah, the agent itself is gonna be a normal program that determines which actions to use. But yeah, whatever knowledge it needs to make those decisions is gonna run through the knowledge base. Yeah, it should look very much like I'll pull up the slide. It'll look very much like the knowledge base agent from whatever slide that is.
Chris, can I be honest? I tried looking at this language in her head, so I feel like you have
That is honest.
the LPK.
I've been using, there's a few MIT assignments that use the same like logic that we're using for their Vermont's world.
Yeah,
There's just like a really baby down version of it, but it's been a pretty good source of what to do. Like what to think about.
it's really like a good source.
I read land account to this language, I'm reading it. I gotta go catch up on that some more. My bad, but
So here's what I'm referring to, the logical inference agent. So this is what your agent code is going to look like. So this is written with a regular script using procedural logic. And you see that the agent is telling a knowledge base and asking a knowledge base as you do this. And then determining a plan based on the information that it gets from the knowledge base about what should I be doing next? So if I ask the knowledge base, do I experience, is the current location glittering? The answer to that is yes, then your plan is to grab the goal and then route out of there. So grab the goal and then plan route from the current position to 1-1. And plan route is its own code as well. You don't have to go through the knowledge base for that. So the knowledge base is only storing the associated, like, is something safe? And everything that you would need the knowledge base to be able to tell you is embedded in this inference agent code. It's just a matter of what do you need to put in the knowledge base in order for it to give you the right answer to that for all cases. So it needs all of the associated rules in predicate logic and all of the associated additional ways of storing things, like if I want to be able to query whether something is adjacent, or I want to be able to query whether something is safe or something else of the sort. So it really shows you everything that you would reasonably ask the knowledge base, everything you would reasonably tell the knowledge base based on when and how.
The knowledge base also handling, if you lose, like if you landed on a pit and died, or.
Yeah, so the knowledge base, yeah, can return something like you're on a pit, therefore something. But if you do this perfectly, then your agent should never run into a pit. So the fact that your agent runs into a pit, you should immediately return like there is some kind of logical error.
I almost want to make like a referee to
Yeah,
play in just normal Python.
Yeah.
To check it.
yes, you could.
I don't trust.
Yeah, just throw an exception in in this code if you query the knowledge base, am I on a pit? And the answer is yes, just accept from there and something.
Except that.
Is this clearer? Does this make a bit more sense? Hopefully, give you a little bit of direction as well, that I'm trying to provide kind of the structure here that you should be looking at for coming up with this agent.
The agent
Yeah.
is the one that maintains the score, right?
Yes, yeah, the agent will know the associated score that it's getting. So whenever it makes an action, there's some global counter that is keeping track of a score. It will start at 0, every action that it takes, -1, -1, -1, -1, until it either shoots the arrow -10, climbs out with the gold. It doesn't get a score for the gold until it climbs with the gold. So just because you've seen the glitter and grab doesn't mean you get 1,000 right away. You need to successfully escape first. And if you fall into a pit or get eaten by a wumpus at any point, -1,000. And the idea is that over time, you should see a positive score, but you should also make sure that you're adhering to the rules, because the easy way to maximize the score is just ignore the rules. The more rules you ignore, the higher score you can get. But that means that your program isn't doing anything intelligent within the confines of the world. It's just returning a score because you haven't adequately represented the world. You haven't adequately represented the problem. And that's how you get into that situation of, our company has not had a security breach in 20 years. It's because you're not actually looking for them. You say you're looking for them, but are you really looking for them? You can make weird claims when you don't follow the associated rules of the system. So being able to represent the rules of the system is a natural way to apply knowledge-based agents.
Because I have another.
Yeah,
Yep.
5 of them. I think they all have at least a little bit of juice left.
Talking about some of them. But our world, right? If our agent starts out right, and we have like, hit, we have an office, we go here, and every time it deducts a score.
Yep.
Every time. And it would say it's explored every cell, and it knows there's gold here, right? We assume that there's always gold.
Yes, there's always exactly one goal.
Okay, it always assumes that we gold, so say it's explored every cell, it has like a negative score at that point.
Yes.
Would it be, if at a certain level, would it assess that it's worth it to get the gold, even though?
It should always be worth it to get the gold. If the gold is accessible, even behind the walls, it should always be worth it. And in this case, if there are no further pits, then we can prove that the wumpus is in that location, which means that we can shoot the wumpus and go past the wumpus that would grab the gold. Even if you're -600 into a run, note that the sunk cost is already -600. It's not like I shouldn't have started this in the first place, I can get back to 0. If you escape without the gold, because you've just been exploring randomly down there, the sunk cost of the -600 doesn't matter. If you can grab the gold and get +100, +1,000 from there, that will be worth it. Rather than take the -600.
Or what if it's like -999, you shoot our arrow, and then it's like negative.
Oh, it's fine.
1,009, and then come out with -9.
The comparator there is -9 or whatever it takes to escape from -999. So you would rather grab the gold at that point, because it will still add 1,000 to your score. And with any reasonable world size, including up to 10 by 10, you would expect to be able to fully explore, analyze, grab the gold if it's possible, and escape. The idea is that you should be getting a positive score overall over a number of runs of randomly generated worlds. Unless you make your pit density so high that every single world has.
What's the size? Gets to. Got like a 10 million by 10.
Oh, yeah.
Roughly.
I'm capping it at 10 by 10 for this assignment, but yeah, if the world gets ridiculously large, then it would stop being worth it, and you'd have to increase the value of getting the gold in order to make it worth exploring the space at all. Or just make the cave full of way more than one gold.
Only there's not island size, like with constraint.
No, I don't hate you that much this time.
Interesting.
Also, one more question. If we have, say, a pit here, right, it moves and goes to 3s.
Yep.
They could assume that there's a pit here. And it's
Yeah, it
saying,
does not know.
and if it tries to go this way, then
Yeah,
it feels a breeze here.
yep,
And they would assume that there could be a pit here as well, right?
right,
So with the optimal option for the agent just to pay them.
yep, because we don't know for sure, anything is a risk.
Even though it's trying, its #1 goal is to get the gold, right?
Yep. But At that point, what is the probability that a pit is in any of the question marks? We'll talk about this eventually, possibly today, possibly Thursday. But the probability that whatever action you take is safe is not going to be worth the risk unless, like, is it equally likely there are pits in each of those locations? The answer is no.
No. Yeah. But it could still.
So there are more intelligent places to explore and less intelligent places to explore based on that. So given the knowledge of how many cells are left unexplored and the probability of falling into a pit, maybe there is an intelligent decision that could be made that it's worth exploring in case there's not a pit there. What is the probability that if I explore that, I'll be able to get the gold? What is the probability that if I don't explore there, what is the expected value of exploring versus not exploring? If it turns out to be a net positive, then maybe it's worth accidentally falling into a pit sometimes. But for now, don't worry about it. If it's unknown, and all unknowns are equally problematic. That is a great point, though. Yeah,
Are the maps guaranteed to be square?
yes, we're gonna say it's an n by n grid. 2 by 2 up to 10 by 10. And I'm not gonna test anything outside of those bounds. I'm not gonna test any rectangles, although that would be an interesting way to attack a user's assumptions is, now it's a rectangle, what do you do? But yeah, I'm not gonna test it, the functionality of your program, anything other than a square.
There are office worlds that include risk, like actual, like how these guys are handling, like risk to reward situations. Where it judges that maybe with a certainty that there is just one hit walking off
Yeah.
in two directions.
We're talking about that next.
Okay.
It ends up using Bayesian statistics.
Oh, it's-
Bayesian statistics?
Yeah.
We haven't talked about anything stats related yet. Anything probabilistic. Who remembers Bayes' rule from a stats class?
Since I'm already.
This, I've seen this somewhere, yeah. Who's never heard of Bayes' rule before? Who failed to raise their hand? It's a yes or no question, there's not a neither response to that. Is the answer maybe? I just wouldn't, I have to see it to know the associated name, it's probably the most likely route. So it's causality in probabilistic inference, so, or conditional probability. But what's the probability of, how can I convert cause given effect into effect given cause? And how can I make an inference from there if I know certain data about the environment? Can I make a probabilistic inference in the opposite direction by mathematically manipulating the result? We'll talk about that. We'll make it much more intuitive.
Didn't Bayes not even want to publish that because he thought it was so obvious and self-explanatory?
Yeah.
It was like, why would anybody need this published? You an idiot, you don't know it,
Yeah,
but it's like everybody messes it up.
yeah. Yeah. It's interesting to think about logic versus human inference. And when you're in the middle of a logical world, sometimes you assume that people are more logical than they are. And that gets me in trouble too.
No, you do what you say, right?
Yeah. All right, so we were way further along in this.
Also, does the agent track if it's dead or not? Is that up to trees?
The agent can track the associated score from the knowledge base. So it's something like the agent knows where it should query something like, am I in a pit? To the knowledge base, and the knowledge base can tell you, yes, if you've designed this well, the agent should never be in a pit. But until you know that for sure, maybe that is something that the agent can query the knowledge base of. Or the world of. You can see it enter a pit and say, wait, it shouldn't be able to do that. It should know not to do that. Where did it go wrong?
But I can have a flag, an agent that says it's alive, and then if it's
Yeah,
true.
you'd have to somehow look up into the world file and have knowledge that is not.
Person, I'm true.
Either that or have a percept, like is dead. The agent perceives that it has perished. We'll call it the pearly gates percept.
We all have.
So last we talked, we were looking at the difference between forward chaining and backward chaining with this redundant inference chart, and we found that there were differences in the number of inferences that we needed to make between forward chaining and backward chaining. And we were kind of done talking about that and ready to go into resolution as the next way to determine logical inference. So as the knowledge base figures out how to ask a query, it's either going to use forward chaining or backward chaining or resolution and some combination of those. This is nothing that you should need to implement within the natural language toolkit. This is something that should already be embedded in it, but you should know how it works, just so that you can ensure that if something is going wrong, where is it going wrong? So all of these are already implemented within that library. It's just kind of plug and play. So resolution, this one's my favorite. First task is to convert all of your sentences into conjunctive normal form. And conjunctive normal form just says that we have ors of a bunch of and clauses. So yeah, conjunction of clause, this and this and this and this, where each this can be things ored together. So a conjunction of disjunctions, if that makes sense. When I woke up this morning, I ate breakfast or I drank coffee. And when I arrived on campus, I parked my car or locked up my bike. And so each is an action of options. We know that all of these things happened, but exactly which one we selected or multiple within each of those is up for interpretation or may vary. Any variables found in literals are assumed to be universally quantified. We can convert anything in first order logic into an equivalent conjunctive normal form sentence. As an example, here's our first order logic. For all x, y, z, if x is an American and y is a weapon and x sells y to z and z is hostile implies that z is a criminal. So there's your first order logic. If we wanted to convert this into conjunctive normal form, we can't have implication as a conjunction of disjunctions. So we convert into either x is not an American, or y is not a weapon, or x didn't sell y to z, or z is not hostile, or x is a criminal. Do we see how, as a single statement, any one of those being false, or how that says the same thing? Take a second look at that and convince yourself that this is stating logically the same thing. If x is not an American, then we say nothing about how x can be a criminal. We only specify the criminality of Americans, no one else. If y is not a weapon, then it doesn't matter if Colonel West sold a Rubik's Cube to No-No. That's not a crime. That doesn't prove that Colonel West is a criminal. So if y is not a weapon, it doesn't matter what anything else is, or if the rest of it holds.
I don't understand how those are equivalent, since any one of those conditions on our right would just equal to one, and it wouldn't even matter if he's a criminal or not. It could just be an American.
Yeah, so what happens if all of these are false? Or sorry, if everything that is here, we invert. So X is an American, Y is a weapon, X sold Y to Z, Z is hostile, and X is not a criminal. That is the only way that that statement is false. Let's see if I can draw this out better. Yeah. So all of these, have to be true. This is the big if. This is the big then. The only time we're making a statement, a true statement about criminal, is if all of these are true. So X is not a criminal if any of these other things are false, or at least we don't have evidence that they are a criminal. So either, let's just come up with an example of, give me an X. Basically, is X an American or not an American?
Not in there.
Not an American. Is Y a weapon?
No,
Did X sell Y to Z?
also,
So we'll just say. And is Z hostile?
Yes,
nothing happened, let's see, it's very hostile.
Yes. And is X a criminal?
No. Not necessarily.
Yeah, so
Says nothing except to.
So basically, this or says that one of these has to be true in order to have meaning in some way, shape, or form. So the fact that X is not an American, this whole thing is true. All of these ors, they're ored together, the end result is true. Think about the implication, the associated truth table here. Is the if portion true? Is X an American and Y a weapon and etc.? Is the if portion true?
in the scenario we set up, no.
Yeah, so this whole left-hand side evaluates to false. If we look at the truth table for an implication, what does false implies anything? It's true. It's true. Yeah, the truth table for implication. We have true, true implies true, false, false, true, false, false. This is true, false, true, and true. Going back to discrete. So I would argue that whenever this is true, that is true. And whenever this is true, that is true, false, 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 false. So this is the implication. We just have to figure out what are the associated variables and how do they map from one side to the other. What does it take in order for this to be false? We need a very particular arrangement of these variables. The left-hand side must be true. In order for the left-hand side to be true, this must be true, and this must be true, and this must be true, and this must be true in order for the left-hand side to be true, because they're all anded together. In order for this to be false, that has to be false. So it's a very particular arrangement of the values of each of these variables. On the right-hand side, this right-hand side, that's immediately apparent in what breaks this whole thing. Well, if this were not true, that would break the entirety of this. So that's how this shows up here. If this were not true, it breaks the entirety of the left-hand side. False implies anything is true. So negate that. If this is false, breaks the entire left-hand side. So if that's false, it breaks the entire thing. Does that become more apparent now how these are logically equivalent? Do we remember why false implies anything is true?
I just remember it as like binary. False, false.
Yeah. It comes from negating it. If we said let's negate this whole thing. There's an obvious result to it. So false implies true says that if this weren't true, then how does the implication work? And if we negate it, it's basically saying, if one of these isn't true, is he still a criminal? In which case the answer is no. We have no evidence that there is a criminal with that negation. So if we negated this to arrive at false to criminal, then false implies true has to be the opposite of that, which is true. Even though it doesn't really have meaning. We don't state anything logically about what happens. There may still be criminality associated with this, but when we negate it, there's an obvious answer. Does that make sense? See if I can come up with an example off the top of my head for that.
Wouldn't the third row be false, true, false, or?
It is actually true. So think of it like, if X is a crow, then X can fly. What we're stating here is if X is, we did a two-parter. If X is a crow and X is black, then X can fly. So if F is not a crow and X is black, do we make any claim about that from just the knowledge of the only statement we have is if X is a crow and X is black, then X can fly. We make no claim about that, but negate this statement to say the opposite of it, false implies true, and the answer is obviously false. So if we have something that is not that, what is the negation of false and true?
That value is false and then not.
It is true, not false or not true. De Morgan's law.
That's what you just did that, well.
Yeah, so this is obviously going to be false here, so the negation of that has to be true.
Yeah. So gross.
If we're not doing this in discrete, I'm sad and crying tears of math.
We are, we're doing it in 160 as well.
Yeah.
We do it twice.
About 4 years ago.
Right. That's okay, I taught this 4 years ago and I have to dredge it up from my memory as well. I haven't touched this since I taught it 4 years ago.
I don't use this as much in my everyday life.
Yeah, right. Yeah, so when we're trying to program a knowledge base agent that utilizes some very corner of your brain, I learned this 4 years ago and haven't used it since. Yep. So the entire purpose of all of that was to say that these are logically equivalent to each other. So we can take first order logic and we can convert it into a conjunctive normal form that allows us to move forward with resolution. So any first order logic we can rewrite to be in this form as a disjunction of conjunctions, where each one of these elements is going to be ands, or some ands, or some ands, or some ands, or some ands, etc. So we would allow ands inside of here, we just didn't need them for this particular first order logic. All right. How about an English version of what we have here? We're gonna learn how to actually convert it into conjunctive normal form. So for all x, for all y, animal of y implies that x loves y, implies there exists a y such that y loves x. Y is an animal and X loves Y, it implies that there exists a Y such that Y loves X. What is the English statement there? We can turn that into an English sentence that sounds like it's normal and not like it's been fed through a logical translator.
Loves X, Y. Where received back. So there's a-
Yeah.
So
So convert it into English. A statement that someone might say on the street.
I love my dog and my dog loves me.
Not quite, but we're getting there.
If I love my dog, at least one dog loves me.
Okay, good guess, not quite right.
No?
I don't think you guys have ever been on a street. Who said that?
Some talking street.
Yeah.
Maybe I shouldn't say street, maybe you say hallway.
Yeah.
We're in Spokane after all.
Yeah, true.
Everyone loves animals, then at least one animal loves someone. Something.
Close, closer.
What are the truth table? What's the truth table for implies again?
It's true, false, true, true for combinations of things. So true and true implies true. True and false implies false. False and true implies true. False and false implies true. But this is an implication with an implication. So the answer to this is that everyone who loves all animals is loved by someone. If you're just an animal lover, it doesn't matter what the animal is, someone will love you. You won't be completely unloved in life.
Is that what you tell yourself?
That's what the textbook told me. This is what I get for listening to a textbook.
I thought that Y represented the domain of animals.
So, yeah, Y is an animal. So some X, every X, such that X loves every Y, since they're both universally quantified. So everyone, all X, everyone who loves every animal. That implies that if an X exists that loves every animal, for every one of those, that implies that there exists a Y such that Y is loved by, I guess, yeah, some animal. It should be some animal.
No, I think the Y is the animal. and
Yeah.
the part, the X is the person.
Yeah, but the animal loves the person back. There exists an animal that loves you back. Yeah, that is better, and I'm just gonna fix that on the slide before I even think to procrastinate that. That's better. All right. Remove implications, we can use the implication elimination rule to do that. Hopefully people caught up on their associated discrete and logic. Implication elimination just replaces implication with not P or Q. Or P implies Q. That's just the equivalent of that. If we look at the truth table, true, false, true, true, either P was false or Q was true. So we do that for the internal implication, then we do that for the external implication. So we go from the top, we remove the inner one first, so we're gonna remove this implication. And that gives us that, not this or that. And then we move the negation outward and then we deal with that from there. So we say not that or the inside. So this becomes the entirety of the right hand side where we have not left hand side or right-hand side, that doesn't change. Does that make sense? So this is the implication elimination portion of converting into CNF. Then we move negation inwards, and the rule for moving negation inwards is that we're gonna flip the quantifiers. So whenever we have a negation surrounding something, we move it inwards, negate the entirety of the internal form, and flip for alls to there exists, and there exists to for alls. That's your rule for that. So going from here, we move this negation inward, negate this entire internal statement, flipping the for all to there exists. Then we can move that negation inward and we flip all quantifiers. We negate the inside and flip quantifiers of what's on the inside. This is still on the inside of something else, so it doesn't change yet. Then we move the negation inwards again. And we get our final result. The double negation here just goes away. Questions on any of that logic? Give you a second to stare at it. Questions? Confusions? Boredom?
Isn't those last two? Wait.
It's because there are brackets around the first part, so this part doesn't change.
Yeah,
We're moving the negation inward here, so moving
Oh,
the
I see.
negation inward, it's gonna negate that.
Yeah.
Negate this, flip that sign. And then that closes the moving the negation inwards from the outer, so this does not change.
okay.
So the part that says, how is this done? The left-hand side implies the right-hand side, that just says the same. Like, I don't know. Informally, it has the same truth table as that nonsense, the fish line on. here.
Yes.
Just because of
Yeah.
that one, 0.1. Right there.
That 1.1,
Sorry, no, the number one sentence right there, yeah. P implies Q with. Not
Yeah.
or Q,
yeah,
that's it.
that's the equivalence rule. So yeah, we're basically taking this internal statement right here and applying implication elimination, replacing the implication with negate this part. So this is negated. This is turned into an or, this stays the same.
We're turning something that loosely resembles English into something that isn't really English.
Yep.
Cool.
So that's what gives us this.
Yeah.
Then we eliminate this as we have the left-hand side. So we're gonna negate the outside or, and then keep this the same.
Yeah.
Which gives us the bottom.
Really quick follow-up question.
Yeah.
Is it normal to not really be able to read? The
It takes practice.
yeah,
No, you
the,
can't.
the original sentence is,
Makes
Follow.
sense. Yeah, and this just starts to make less sense.
yeah,
But the idea of converting into first order logic is so that we can apply resolution. And we will see the actual power of resolution very soon. But in order to apply resolution, it has to be in this form. If it's not in this form, we can't apply resolution to it.
Oh god, you're gonna have that on the test.
That's what I came to that realization, and the loss of hope was.
I'm gonna try to keep what is straight discrete off of an exam in here, but instead talk about something like, how do we apply a resolution? Even that's kind of a discrete, but
Yes.
how is all of this used to create a knowledge-based agent? That's kind of the level that I will want to target. The rest of this is just discrete redux. Or if people haven't seen this in discrete, what discrete should have covered.
It's the thing that false implies true, false implies false,
Yeah,
that
negate it and it makes much more sense.
They should just have you teach every
that's
class.
doesn't make more sense, true doesn't apply true.
Well, it's not even negating every aspect of it. If you have something like false implies false, something like if 1 + 1 = 3, then bears can fly.
Well,
That doesn't make sense as a true statement or a false. Is that statement true or is that statement false?
Both parts are false.
If 1 + 1 = 3, then bears can fly. This is false implies false.
and logic, how do you say it's a?
So, yeah, let's just write that. If 1 + 1 = 3, then bears can fly. I like that as a. This almost makes no sense to talk about, right? Is that a true statement or a false statement? It doesn't really have meaning, but negate it. What happens if we negate this statement? So first, let's remove this implication. This basically says 1 + 1 = 3 implies bears can fly. So we said the negation, or the implication elimination of this is either not 1 + 1 = 3 or bears can fly. Which one of them is true? 1 + 1 doesn't equal 3.
Yeah.
So this entire statement is true. Because this is false.
Yeah, man.
If you wanted to negate this, then what you would be saying is, let's negate this and see if it actually has real value. To move this negation inward, we get rid of this, we flip this negation, we flip this into an and we put a negation here. So this tells us that 1 + 1 = 3 and bears can't fly. That's obviously false. So the negation of that has to be true.
Wouldn't it be 1 + 1 = 3 and bears cannot fly?
Yeah, because you're saying.
Yeah, not bears can fly,
Okay.
so bears cannot fly. Did I say bears can fly?
Yes.
Cannot.
Why do we want to check the truth value of the whole statement itself?
Because a knowledge base would need to be able to determine, can I prove this? Can I prove that some false statement implies some other false statement? That might be something that you ask. And every statement is either true or false. There's no statement that is both true and false, and there's no statement that is neither true nor false. There's a truth value to every statement, every logical statement. So if you're working with a knowledge-based agent, you need to be able to determine the truth value of any statement that's given to you.
It's tough for me because it's like the symbols are saying something that's not intuitive, and I'm trying
Yeah.
to backtrack and put something that intuitively makes sense on top of it, but it doesn't really give a shit. It doesn't care what I think. Or
Yeah.
whether or not it's intuitive, it just is.
Well, it needs a truth value,
Yeah,
right?
oh, it just is.
If 1 + 1 = 3, then bears can fly, needs a truth value. And it doesn't really matter what value you assign it until you think about the negation. And the negation has an obvious value, and if you negate something that is true, you have to get false. If you negate something that is false, you have to get true.
So would you say it would almost be more useful to remove all the extras, so you just say 1 + 1 = 3, we'll just represent with A. So A and not B,
Yeah,
yeah,
yeah, you can just turn this into a left-hand side and a right-hand side. This is your P, this is your Q.
Okay.
So P implies Q is the same as not P or Q.
and it's almost irrelevant from the side.
Yeah, it's either 1 + 1 does not equal 3 or bears can fly. And obviously, neither of them are true, so it doesn't really matter which one you try to select. The entirety of that statement is false. Sorry, the entirety of this statement is true because 1 + 1 is not equal to 3. In which case, if we negate it, then we find that both 1 + 1 = 3 and bears cannot fly. Which is obviously false. So if this is false, then the negation of that has to be true. I taught this over COVID, it was a nightmare.
Or blank screens.
Yeah. It's kind of like looking out at this class.
Very reminiscent, I'm sure.
Does this make sense at least though? If we reached a point where hopefully everything that is here, we have the necessary background for. All right, so diving into what resolution actually is the original meaning of the sentence preserved? Either there is some animal that X does not love, or some animal loves X. I didn't say someone, it should be some animal loves X. That makes sense. After the implication elimination, that's the same logical statement. We're not making any claim about people who don't love every animal. So either they don't do that or someone loves them. Because they love every animal, which is the negation of the first half. So yes, we have preserved the meaning. The next stage, standardize our variables. If we have variables that represent different entities, they need to be distinguished at some point. So if somewhere along this, we refer to an X or a Y and then another X, we have to make sure that we have an X1 and an X2 unless they have to refer to the same variable.
I'm confused how that preserves the original meaning. Because the original meaning is like if any animal, or if you like every animal.
Yeah,
Some animal likes you.
everyone who likes every animal has some animal who likes you.
Sure, and then this is saying that
Either there is some animal that person does not love, or someone loves that person. And the only way that someone would love that person now is if that left-hand side is false,
which is they love all.
which is they love all animals.
Okay.
Yeah, so that's just kind of the logic or the intuition behind implication elimination. The way that the if then breaks is if the left-hand side is true and the right-hand side is false. So either the left-hand side is true or the right-hand side is true. So here we have different versions of Y, and I think this is where this comes in, where Y loves X. That's why. I actually should go back and rechange the slide. So the fact that this was separately quantified, there exists a Y, and this for all Y that used to be for all Y that was flipped from that says that those Y's are different entities. So because of that, we need to standardize the variables so that if we're using the same variable under different implications, then we change one of those variables so that they're not referring to the same idea, because Y is not necessarily referring to the same Y, which is why it was confusing to you, and I had forgotten that. So this makes that make way more sense. Because we want to be able to standardize eventually. The person who loves X because they love all animals isn't necessarily an animal, because they're separately quantified. As you scholemize, this can lose the original sentence's meaning. So scholemizing is removing existential quantifiers. When we know there exists something, we can just make a new constant that represents that idea. There exists a student in this class who something passed the last exam. Rather than identifying which student it was, let's just make a generic entity, that student who passed the exam. There may be more of them, but now we can just talk about it as that constant, the student who passed the exam. So sometimes this does lose the original sentence meaning because the there exists says some and there could be multiple. In fact, it could be everyone. But it says at least one. So scolomizing is doing that. So this would get rid of the associated animal A. Note that we did say for every animal, this just says because there was a there exists on that animal, for all X there exists a Y such that Y is an animal and X doesn't love Y, or there exists a Z such that Z loves X. That's just saying the same thing as we did before here. So scolomizing is saying for every there exists, let's replace this with a constant. There exists some constant. And now we have a constant wherever we refer to that A, and this B. As the entity for which that there exists referred to. Now it's not a variable anymore, it's a specific abstract concept. The student who passed the class. The student who passed the exam, whatever. Questions on scolomizing? So we've now changed the meaning a little bit to say everyone either fails to love a particular animal or is loved by some entity B. And now we have changed the meaning a bit by scolomizing. It's a subset of what was originally intended. By the time we've done this, all remaining variables have to be universally quantified. We've gotten rid of the existential quantifiers for everything as we convert this down into CNF. Finally, since everything is left that is universally quantified, we drop them. And we end up with some statement that has ands, ors, and nots. We then just have to distribute. And the result is something that just is not particularly readable. Either f of x is an animal, or g of x loves x, and x doesn't love f of x, or g of x loves x. Wonderful logical statement that just is so readable. But when we reach this point, we can start to resolve some things. Let's take a look at what resolution actually is and how this can derive new information, new truths out of an environment. So the goal with this is that we're going to insert a statement into our knowledge base. Then we're going to attempt to resolve this against everything in the knowledge base with an attempt to derive the empty clause. If we derive the empty clause, this is like a proof by contradiction. We have a contradiction in our knowledge base, and we know that the data that we entered has to be false so that we can enter the negation of that as truth. So have we seen or remember proof by contradiction? So something like you can assert that the square root of 2 is rational. And we can just proceed logically from there to derive a contradiction, something that is both true and false, or neither true nor false. And if we do that, then the only statement that we made that we didn't know the answer to was that the square root of 2 is rational. Therefore, we can conclude the opposite of that, that the square root of 2 is not rational. And that becomes a proof for something like the square root of 2 does not repeat ever. Wouldn't it be nice if we could say the same thing about pi? The square root of 2 will go on forever and never repeat. And it boils down to a simple proof by contradiction. We end up being able to say something like, if we know these two statements, so the entirety of this left-hand side is true, and the entirety of this right-hand side is true. What resolution allows us to do is see these two statements, kind of combine them. We can instantiate u to g of x and b to x, cancel them together, and we can derive f of x of an animal, or u, whatever the u instantiation was, g of x does not kill the instantiation for b, x. So we derived a new left-hand side here, or the right-hand side, as a new statement that we did not know before in our knowledge base. So resolution is a way of saying, if we have a statement and the negation of that statement inside of two disjunctions, we can cross them out or everything else in those two statements and insert that as a truth. Let's see if we can understand intuitively why that is the case. Let's come up with something more relevant than this left-hand side and this right-hand side. So someone give me a disjunction of some or that makes that you can attach yourself to. This or that.
Are we doing or commands? No.
Something simple like coffee or asleep. Now, let's and that with another disjunction where one of these is negated. Someone can pick one, either not coffee or something else, or not asleep or something else. Give me something to work with. We're gonna negate one of these two things and or it with something completely different.
Not asleep and driving.
Not asleep or driving.
Or not driving.
I'm either not asleep or I am driving. Not driving. So what resolution would tell us that we can derive a new fact from these two ground truths. We know that one of these is true and one of these is true. How is it possible for one of these to be true and one of these to be true? If we start to not care about whether we are asleep or not, that's an irrelevant variable to us. What can we say about coffee and driving? In this case. We can say either coffee or not driving. And we've removed sleep from the entire system. And now convince yourself that this is logically equivalent to that. Or this, if this is true, then this has to be true. So there are possibilities for all of four of these. Either this is true and this is true, which means this has to be false. And then this is true. So these are related to each other. There's one value for asleep.
Yeah, because you're implying that the entire time you're not asleep, you're drinking coffee. And, I mean,
Yeah. So you remove sleep from the system and you can assert something about the other. So in this case, the asleep doesn't matter. We have true and true. I have coffee and I'm not driving, so this statement is also true. Because this statement was true. There's a true here and there's a true here, so this statement was true, and that statement is true because both elements are true. Now let's say that not driving is false, so we would have the exact same thing, true, true, false. And false here. It turns out that what's the value for asleep doesn't matter. Because it's not going to change the value of what's there if we change those two things. In this case, now coffee is true and not driving is false. Is this statement true? No, because we have false or false, which is false. False and anything is going to be false. So is that coffee or not driving? true. Sorry, this and should go over there as well. But resolution works like that. Sense? How are we doing? Yeah. So this works for arbitrarily sized logic as well. We can use resolution, and it becomes the way that we use proof by contradiction to assert something to the knowledge base. When we assert something, we can propagate it via resolution down into, can we derive a contradiction? If we can derive a contradiction, then what we asserted has to be false. Assert the other thing. And if we assert something that is false, it'll resolve against everything and eventually derive that contradiction, where we have something that looks like true and not true, which resolve, or true or not true, which resolves against itself to get empty. And if you can derive that, then you're good. So insert a statement into your knowledge base. If resolution can generate the empty sentence, the statement is not consistent with the knowledge base, and you can assert the opposite of it if it's a binary statement. So here's an example. We know that here's what we derived with regards to the statement for, we went through converting this into conjunctive normal form. We're going to assert the opposite of what we want to prove, that West is not a criminal. So we can resolve that West is not a criminal with this criminal, deriving that, everything else from there without the criminal. Then we know that West was an American, so we can resolve that with not American West and generate just what's left. Missile X or weapon X, that resolves with not weapon Y. So now we can get rid of both of those and assert now the not missile comes into this because we take the everything that doesn't have to do with weapon and or it together. Now we know that M1 is a missile, so we can take that with Y, instantiating everywhere else there is a Y with M1. Resolve that, gets rid of that, leaves us with just this. Now we can resolve cells West X no with West M1Z, and we have the other instantiations that we need for everything else. We order together missile, not owns, and not hostile, and that's what drops down to here. Resolving missile M1, resolving owns no M1, resolving hostile X, resolving enemy no America, and we generate the empty clause. So it's a many step resolution that involves a search through your knowledge base. But as you do that, you can assert something that you don't know. And if you can generate that empty clause, you know that it's not consistent with the knowledge that's in the knowledge base. So you can assert the other because you've proven that the negation of that is false. The assertion that West is not a criminal is false, according to your knowledge base. And you know this because you derived a proof by contradiction from it. You derived your contradiction. How we doing? Does that make sense? Does the process of how to apply the resolution make sense? A bunch of nothing.
More than it did before.
You have fun walking and turning.
Yeah, right?
No, Steve. I have a logical proof about it.
Yeah. You have to phrase it differently, I'm sure. But if you're writing a program that's trying to prove something like whether a security vulnerability was exploited, yes or no, with the associated evidence, you could assert something like, given the evidence that is here, derive down to the empty clause, in which case, with the associated data in the associated data logs, you would be able to resolve against all of that and derive that, no, the evidence is actually there. Something you could do. Last thing we have here is an example. So let's take a bit of a break. I want people to come back with fresh minds to handle this example of going through and converting everything and then applying resolution to it. So we'll get an example of this before we move on to the next exciting topic. But yeah, let's take 5 and come back in a bit.
You could drop a cinder block on my head, Chris Kane.
I did not take.
Fan of $200 limits.
Kick Daniel out, like, Mr. Electro, send Daniel to the principal's office.
Oh, no, I have to talk to the.
Yeah, there was 2DH, if people are familiar with the Seattle version of Commander, there's 2DH where no card is allowed to be worth more than $2 and it's a rotating format, whereas soon as they can, just within that community, everyone wants to buy a card when it's shown to be good, which pushes the price over $2, which makes it illegal in the format. So it's a nice rotating format. If anything that really becomes popular is immediately banned. Unless it is so common that everyone can buy in at that associated price, which makes it an affordable format.
I don't
We
know.
should do
if
that
you-
for everything. That should be like everything residents. Somebody gets too popular throughout.
Yeah, exactly.
I don't know how often you look at like EDH rec, but every time I go to like, a card within like a certain color scheme, it's always like the same blue cards
Yeah.
that are always recommended. And they're like god awful expensive, like Ristic Study is like $80.
It's absolutely ridiculous to me because I bought, 20 copies of it at $1.50, something like that.
It's because you play on the day of the column.
Yeah,
Yeah.
that wasn't in that day and age. That was,
Print as a rare.
yeah,
Not print as a column. The only set that had that is Wild Bone Grand.
that's prophecy, I think.
Wow, is.
Yeah.
That's related to the animator.
All right, let's get you working. So here are some facts.
Loves all in.
Everyone who loves all animals is loved by someone. We already have that one, thankfully. Anyone who kills an animal is loved by no one. Jack loves all animals, and either Jack or Curiosity killed the cat who was named Tuna. So let's start by converting into first order logic. So you can use quantifications for all there exists. You can come up with predicates, loves, kills. Cat. So start with that.
So the first one, isn't that just the same thing that we just did in?
Yes, yeah, so you should already have that as an example. And that's by design, so that you can use that as a reference.
Then second one would be like some subset of people. And then, and kills and animals, is then equated to, not love.
So the second one is you should remind you of implication.
Yes.
That's an if then. If someone kills an animal, that implies they are loved by no one. Then they are loved by no one.
So Chris Kane, explain to me why I haven't killed an animal and I'm still loved by
Because I didn't say this represents reality. This is a toy example for you to get experience with writing first order logic.
I give you that.
And Basil's county.
Am I right? That's like some subset. Like subset, for a second, some subset of people, right?
Use there exists. If it's not universally quantified and we know there exists someone. You can use implication to say, if there exists a person who kills an animal, then for everyone out there, they don't love that person.
That's,
What are you whispering about over there, you
Oh,
fiends?
Don't worry about it.
It's just nonstop humor over there, isn't it?
Oh, well, before he has this like. Why keep years going?
How is that relevant to what we were doing in class? No wonder people
I
struggle.
were wondering why I was laughing, I just like, something catches the corner of my eye that's so, there's a bunch of posters on. All right, class one. Sorry.
Looks like VS Coach when you're trying to hide.
Oh, me? Sim station. Christopher Long, dude, I get that teaching come here, my brain's fried.
Mine too. I force it to work.
I don't think it was talk.
Why are undergrads valued more than graduate students?
Hmm?
Why are undergrad students valued more than graduate students?
They shouldn't be.
Graduate.
More so different there, but
Yeah, but we always have classes in the afternoon.
Yeah, this
Yeah.
did overlap with something that was relevant. I remember having to agree to this. And it was because there was no better place on the schedule to put it.
Well, Sue's also making three of us teach, and I don't think you wanted to say no to that, and you'd rather have this earlier if it was possible. Does that make sense? I think you'd rather have us three teaching in this class.
Yeah.
We have to teach at those hours, and that counts as a half, right? So, cool. I also make David. I go. Count them.
As you convert these, you will also need some additional facts so that everything works together. Do we have an answer? Or at least everyone has written something down?
Well, why do you need additional facts? I don't think you do.
We'll see.
Is that everyone?
Yeah, it loops. Cause you can prove, well, I guess you can't. No, you can, cause you can eliminate Jack from being an option for the person that killed Cat, so it has to be curiosity based on that.
No, you can't actually, because even though Jack loves all animals, it doesn't mean that Jack won't kill any.
No, it is because he loves all animals, so he's loved by someone, therefore he couldn't have killed an animal or he would be loved by no one. So because he loves all animals, somebody loves him, so he can't kill an animal, so curiosity killed the cat.
Like curiosity isn't defined as a person.
Yeah, that doesn't matter.
Also, right?
You don't need to define curiosity because you've already eliminated Jack, so the only option left is curiosity.
And that is the associated logic. But now going from a human brain that is capable of parallelizing all of that into a knowledge-based system that can make those associated connections,
It's just not,
that's what we're trying to do.
the human brain's obviously better. Why are we
For
focusing on
this. In that case, well, the computer's brain is obviously better at a million random math problems. I'll give that to you to do on paper.
No, just put the,
I'll replace studying how to make a computer do this with how to make a human do what a computer thinks is easy.
no, it's the opposite. Let the computer do what it's good at and let me do what I'm good at. Or
How
put a
does the
computer in my
computer do what it's
brain,
good at?
put a computer in my brain. So problem solved.
We spend too much arguing and not enough time thinking.
I haven't argued nearly enough, Chris Kane.
All right, here's what we want. We had the first one. For all X, for all Y is an animal, it implies that X loves Y. And that implies there exists a Y such that Y loves X. And a separate implication, sorry, a separate quantification there says that the second Y is not necessarily the same entity as the first Y that is under the for all implication. B says, for all X, there exists a Z. Z is an animal. If Z is an animal and X kills Z, it implies that every Y does not love X. That says anyone who kills an animal is loved by no one. Everyone who kills an animal is loved by no one. Jack loves all animals. For all X, if X is an animal, then Jack loves it. Then we either see Jack kills tuna or curiosity kills tuna. One of those two statements is true. We need the statements that tuna is a cat for consistency. And we need to say that if X is a cat, then X is an animal. So we need those for consistency, otherwise there's no way to logically connect the concept between Jack loves all animals. Is a cat an animal? Unless we can show that, then there's nothing that says that Jack loves all cats.
So technically I was right, just the initial statements we had.
Yes. Without additional interpretation that is obvious to people who live, but not obvious to a machine that doesn't have any connection between these ideas. And that becomes one of the big challenges with writing knowledge-based or logical systems, is we're going to make assumptions about what the computer can infer, which is the same in any intro programming course. Well, I think that, why can't a computer make that connection? You haven't defined what that connection is. It's obvious to you, but it's not obvious to a computer. Therefore, you need to draw that connection. Logically, it's exactly the same thing. Next, let's convert everything into CNF. So I'm going to give you some time. Let's do our best to convert things into CNF. Do you remember the steps?
So long.
You're right, we should have taken a break.
I think I'm just gonna be a plumber. That's it. I guess I already have the degree. I'm just gonna be a plumber.
Well, they're.
No, being a plumber can't possibly be as hard as being a welder. Being a welder requires skill. Being a plumber requires, like, I don't know, a plunger.
Sure, try it long.
I've done a little bit of it. The easy parts.
I'll put your backup that you were plumb out of luck in CS.
Finance, 'cause
My brain does. Would it be useful to people to go back to the slides of the steps?
Yeah, I don't remember what's the other.
probably.
All
So
right,
even your TA is like burnt out.
I know. I'm burnt out too. That's the nature of, I've been teaching since 9.
You didn't hear my joke earlier. It was supposed to be a curse.
So there's the first slide.
Or
First step, remove all the implications.
Fuck.
Second step, negation inward, flipping quantifiers.
okay,
Whatever that means.
so remove implications.
For all becomes there exists becomes for all. You apply the same logical rules that you do when you move inward. If you have an or an and it's inside of that, then that flips as well. Then we standardize our variables. Then we scholarize. Then we drop universal quantifiers, distribute, and we're good. Lovely 6-step process. What's unfortunate to me is that we have classes like discrete that we just somehow don't utilize up until that point. It's like we think that by describing the actual uses for what people see, it's going to be too much and we scare them away. I'm a fan of you introduce something and then you immediately apply it.
And then you scare your students away. Because
You could just do all the math courses first and then just do learning stuff later.
Yeah.
Just have like.
I think what's happened is we've separated CS from math by so much that it becomes accessible to take CS curriculum without it, the math has been stripped from it.
Yeah.
Well, it's because you don't need the math for programming, you need it for science. Those are two different things.
Yes,
And.
well, to understand, to design things, you need the math, to be able to show why something runs at a particular time, to intelligently write the right program.
Yeah.
And I don't think we did a lot of that, ever.
Yeah, that's a
Like,
problem.
I got,
That
like,
belongs everywhere in upper division curriculum.
I don't understand, like, I mean, I've never been
software.
I've never been good at math. But like, some of it's like innate stuff. If you like just understand it, you don't, like, I couldn't write this out, but I could break down the problem, right? Is what I'm saying.
Sure.
So it's like two different things. I can
Still,
still,
one's something that you've learned how to do, and one's something that you don't really have experience doing, but if you
Yeah.
had experience, it would be a second.
no, well,
nature.
that's what I'm saying is like, it's not required to write it, right? To, if I need to write a program, I just need to program the program. And if I can think through the programs enough to write it, boom, the assignment's done. I never had to write this.
Right.
So this never came up. This was never checked. This skill was never built upon.
Yeah.
And I got through my entire degree without looking at it one more time. Now we're
Yeah.
masters and it's back.
Yep,
This has mostly come up for me when playing with Minecraft Redstone,
Oh.
no other case.
I did hear, I did hear, I remember I worked at a place that makes chips here in Spokane. And that's, the guy's like, oh yeah, just think about it like redstone. I'm like, I don't ever do that. I suck at it.
You got a single inverter and then you just build it.
okay. This or the one before?
One before. Okay. Okay, it was one after, sorry. Thank you. Yeah.
Like from, you like learned it all from the ground up, there's like Java, there's Python, there's C, which goes closer to the Java, and there's assembly, which goes really close to it, but then there's like this gap between like. First order logic and everything that does that.
Yeah, I don't know, I didn't take a Python class here. So my experience is like Java, and then I got to real classes and they're like, cool, you know how to program in Python. So I'm like, oh, I'll learn Python. And that was like Tony, and then Tony taught me how to actually learn, which is cool.
I think C should be filed.
I think it should.
C was my first language.
I don't remember C at all either. It was one of those like one-off classes like discrete that I had to suffer through, and then my brain promptly forgot because it sucked. And I've never touched C again, other than
I think the
reverse.
issue is, we need to teach language theory so that it's not about which language you know. If you understand the inherent similarities between languages, it's like learning a second language, learning a third language. If you understand grammar rules and how meaning is constructed, then you can learn any language much more quickly. And it involves a lot less random memorization, because you understand, oh, this is just a Latin root for, I understand why that is. It's just less memorization. You can start to understand the why behind the language's construction, the associated rules of the grammar. Oh, this is like that. This makes sense how this comes together.
It's like-
It's very similar in, there's logic behind every single programming language. There are design decisions behind every single programming language. You'll do a lot less syntax and semantic memorization if you understand, oh, this is how they represent this idea. I get it now. I see why this design decision was made for this language. It's for this use case.
I concur.
I disagree with that.
How so?
I think that's teaching bottom up, and I think that's the deception of, much more intelligence of the learner. I like.
Yeah.
Almost an absurd amount of intelligence for the learner. I tutored for church in Java.
Mhm.
The vast majority of the students are just learning the concept that the computer has idea of an object that is
Yeah.
comprised of primitives, which are actually just locations.
Yeah.
They
should not start there.
Yeah, and like, they truly do not understand how a computer language functions. So
Yeah.
you want the one that looks the most like English, and then to walk them closer to the concept of an abstracted language, which is the
Yeah.
theory.
Yeah, the programming language concept should be at the 300, 400 level.
Okay, yeah, I was gonna
Yeah,
think-
100, 200, even through data structures, I think has to be a single language. But by the time you hit something like a master's program, I would ideally like students to have an understanding of here is programming language design, the study. So that if you were prompted with something like, what's the right language to solve this particular problem in? It wouldn't just be, here's the one language I know, or here are the 2 languages I know. You'd be able to say, I understand the design decisions behind 10 languages. Even if I don't have great readability or writability in them, I can see why this should be a Rust application, because reasons. And you can see the design behind the languages. Go learn Rust because you understand how Java and C's decisions are related to a higher level concept. You can now learn a 3rd language way faster than you learned your first 1 or 2 because you understand how language design works. And that is better for students who have taken compilers. It's better for students who have taken a programming languages course that we don't offer here.
So,
For people who have programmed in paradigms that aren't just object oriented, if you have some kind of procedural knowledge, data-driven knowledge for SQL, functional, if you've taken a Haskell, done something in Haskell, done something in F#, done something in OCaml, or done something in a, oh my gosh, what's the term?
I thought it was to do functional.
Yeah,
so.
yeah, and Java now allows for functional programming. C++ is starting to allow for functional programming, but my guess is that very few people in here have ever written anything in a functional paradigm.
I don't know what that is, but I'm a bad student.
So what you're saying is, once we get all land-based, you don't have to trigger that way, then you should focus on the harder languages, also like its spaces and setting up.
No, those are jokes.
The rules for like the something. Oh.
Some rules for what, sorry?
Changing like B and things, but they're pressing that.
For B, like the example for the, yeah.
Shows how to program in Haskell.
Yeah, really fun. You can see.
There it is, oops.
2 things,
Yeah,
we leave PHP out of everything. I like that idea.
yeah,
Also-
logic languages are another paradigm. That's the point that I was gonna make
Also,
before, is that
is
something like. Something
PHP is
like,
logically terrible, yes, but can you go over all the examples?
yeah. So I have to kind of reveal everything to do it, but let's actually go through exactly how that works. So. We did the first one. So for all X, there exists a Z, animal Z, and kills XZ implies for all Y, not loves YX. Let's actually go through that. So first step is to remove the implication. So we need to figure out where is the implication. We have a left-hand side that is that, and a right-hand side that is that. So parentheses, brackets, etc. replace everything. So we want to be able to say that not the left-hand side implies the right-hand side. So we need to negate the entirety of this left-hand side. So we're going to have, where do I want to draw this? Board space. Not, big set of parentheses, for all X, bracket, there exists Z. I'm just gonna say A of Z, animal of Z, and kills X, Z. So that close bracket, or the left-hand side, for all Y, not loves YX. So there's the implication elimination. We have not the left-hand side or the right-hand side, and this should close that, sorry. And then that can also have parentheses around it, but it doesn't matter. It's the same thing. So there's implication elimination. What was the next step? Negations in words, flipping things. So this is inside of that, so I need to move this negation onto that. So the first step for this is we're gonna remove this outer parentheses. So moving the negation to this point here, we're going to flip this quantifier, negate this. Everything else stays the same. But now the parentheses are gone. Or, and there's no negation here, and this doesn't matter, negation is on the terminal. The issue is there's still a negation on something that needs to be moved inwards. So there's another step to that. We now have, there exists an X, moving this negation to this point is going to flip this quantifier. Now the negation is on this entire internal A of Z and K X Z. And there's no easy way to distribute this negation at this stage, although we could. Actually, I think we are still going to want to do that. Or for all y, not L, y, x. Moving this inward is going to negate each of these and flip this. So last step, exists at x for all z, A of z, that gets negated. Or negate the k of x, z, or for all y, not L, y, x. Cool. Step 2 done. Move the negation inwards everywhere. What was next? Standardized variables. So we had a quantification in here and a quantification. Oh, no, there's no y here. So there's nothing really to do here. There's an x and a z. I guess there's this, but this x doesn't have a quantifier. It's still associated with this. It's underneath this. So I don't think there's anything that we need to do there.
What was that, sir? Sorry.
To standardize constants.
Okay.
So it's saying if there are two different definitions of x, they're under two different quantifiers, then we need to differentiate the symbols somehow. But there's only one x quantifier, one z quantifier, and one y quantifier. Before, we had the y quantifier and y quantifier, so because of that, we had to differentiate this y that refers to this quantifier and this y which refers to this quantifier. All right, next, Scolomize. So for every there exists quantifier, we need to create some kind of constant for it, dropping the existential quantifier. So there exists an x, we're just gonna make that some entity. We're gonna call that A, which allows us to drop this. And everywhere we see an x, we're just gonna put that quantity, that entity A that represents that. Now everything else is universally quantified, which means that we can drop the universal quantifiers. Right, next step, drop universal quantifiers.
Yes.
So now this goes away. That goes away. Now all we have left to do is to distribute. But there's nothing to distribute, there are no ands here. But we did need, yeah, this x and f of x. This ended up scolomizing to the fx of x, x. Is this, this isn't this. Where is this showing up?
Or we did it wrong.
No, not necessarily.
I think it's B, it's just
Yeah,
flipped.
it's V, but it's not gloves or not animal or not kills. Yeah. So it is this. We came up with these before, but yeah, B becomes that, which does map to this. There's one example. I think that's the hardest remaining example as well. Because C is just an implication elimination. Not the left-hand side or the right-hand side. D is already basically in that form. E is already in that form. And F is just an implication elimination, not the left-hand side or the right-hand side.
Yeah, if you're gonna give one on the exam, I prefer E.
It won't just be one, it would be more of a convert this into something more involved like
And
this.
that would take 2 hours.
It would not if you study.
You're a bad man.
So once we have them in this form, going through this logic to convert that into B's form, then we can actually go through the resolution, because when we have them in conjunctive normal form, we're ready to just start resolving, because we can assert the thing that we want to show is not true. So we could say something like, that curiosity does not kill tuna. That's a statement that we could assert, that we have no idea the validity of, but everything else we know as part of our knowledge base, based on the ground truth of the world from our first order logic. So we just start to resolve things, generating new statements as we go, which resolve things. And we see that we kind of have a reverse tree that eventually generates the empty clause. And the assumption that we can make from this is that the one thing we added to the knowledge base, that curiosity is not what killed tuna, has to be false. So we negate this and we can assert that curiosity did kill tuna. It was not Jack. And that goes through all of the logic that Thomas went through, but in an automated fashion.
I think I was more efficient.
I'll give you a knowledge base with millions of things in it. And we will see that that does not scale.
We'll let the machine
So
do that.
the diagram showing that it negates every one of the yellow ones. No way.
So yeah, we're taking this blue and this, whatever color this is, we'll call it orange. And cat tuna, not cat X. We can instantiate X for tuna and say that tuna is an animal from that. It's just everything that was here minus this negated with that. So if these go away, that's what remains, instantiating tuna for X. Then here, this and that, not kills curiosity tuna, resolves with kills curiosity tuna, which says that Jack killed tuna. And we continue to this and we generate empty, which means that this assertion is not consistent with the knowledge base.
And so this is what we're doing for the Wumpus.
It is what should already be implemented for you in the natural language toolkit, which is why we can import and use the natural language toolkit. I just want to show you what it's doing underneath the hood or behind the scenes for how it works.
Built in there.
Yes, all of the associated logic part is embedded, which is why it's so easy to use, is it automates all of this for you. So it's always good to know how something works underneath the hood, but once you understand how it works, you don't have to think about it again. You can just use it. It's a tool that can be used. Yeah.
So I'm kind of confused about where the. If we're calling the blue and the tan come from, I see the very top one, not cat or animal. Looks like it's, if it's a cat, then it implies it's a.
One of these. Yeah, we use the implication elimination of cat imply, or sorry, tuna is a cat. Cat X implies animal X, etc. And when we converted that into CNF, all of the blue and or orange is one of these. Or something that was derived. So everything that starts on the top is either what we're asserting that is false, or everything that comes directly from that knowledge base.
Okay, so the very top right, not kill curiosity tuna, that's.
That's what we're asserting
Okay,
to try to determine the truth value of. If it is false, then we'll be able to generate the empty.
yeah.
Since it is false, we can assert the opposite of it, since it's binary.
Okay.
Either curiosity didn't kill tuna or curiosity did kill tuna. We can't have both curiosity did and did not kill tuna, or curiosity neither killed tuna nor, never mind.
Yeah, we found the contradiction.
It's did both or does neither. Neither of those is possible. It either did or didn't.
The diagram itself was just confusing.
Yeah.
Thank you.
So there we have it. Questions on that process? If I'm writing an exam, I would feel bad about putting something like this on the exam because it's something that you can just import and use. So I feel like it's not the most relevant skill to test. That's why I want to make sure that I cover enough material that what I do throw on an exam is something that you would actually want to know moving forward in a way that is useful to you in an applied sense and not just a regurgitate the process that was shown for how something works.
That's what I appreciate about you, Chris Kane.
I think we
So-
should have this handwrite all of the one bits were on the knowledge base.
I agree.
That's in full logic.
This is what we have computers for. It's the same thing as putting on an exam, be like, a computer can do this in 1 second. I give you 1 hour. This is a good deal, right? It's funny how many 210 students would agree to that. All right, we're basically at time, so I'll call it here. We'll come back and talk probability. Next time, diving into Bayesian statistics and then Bayesian networks as a way of representing Bayesian knowledge in larger scale knowledge bases. How do we incorporate probabilistic knowledge into this whole system? Well, I'll see you on Thursday for that. Come with caffeine.
This is 8.5.